In this video, I am going to talk about the new gravitational potential energy function that you use when dealing with situations where you're very far from a planet using Newton's universal law of gravitation, as opposed to when you're close to the Earth, which is called the old method. So let's compare the two. So in the first semester, the old method for potential energy, if I had an object above the ground, right here, let's say, we would say that the force of gravity, the x on it, is mg. Right here, pointing downwards. Okay, and I'll do my analysis up here. So step one, the amount of potential energy due to gravity is equal to the force at x. In this case, F is a function of y. For the y-axis, we're dealing with this object is a distance, let's say y above the ground. And let's see here. So this would be the integral of mg dy. The force of gravity dy. There's actually a dot product in there, but I'll ignore that for a second. And if you integrate this guy, you get mg y plus a constant. Okay, so this constant, so this looks like our potential energy function, but this constant, how do we find that? Well, this has to do with our reference line. So when we do these problems, we usually say the reference line is down here at the ground level, right? And what that really is that's potential energy is 0 at that point when y is equal to 0. When we're not above the ground, potential energy is 0. So if I do this, potential energy is 0 when y is equal to 0. So that implies, let's see, if this is 0, that goes away. So that implies our constant is 0. And so really, our potential energy function is the one we've been using, mgy. That's where it came from. Okay? So that's our result there. Okay, so how does this differ when you're very, very far away from the Earth and you're using Newton's universal law of gravitation? So I'm going to draw the Earth here. I'm going to try and line this up so that the Earth's surface lines up with this one for the comparison purposes here. And let's say we have an object above the Earth's surface. Now this is very, very far away. We're talking hundreds of thousand kilometers versus maybe 10 or 15 or 100 meters. This force of gravity is not simply mg, because as you go further away, gravity decreases. It's actually g, the universal gravitational constant, times big M, the mass of the planet, times little m, the mass of this guy over here, divided by r squared. R squared being the distance between their centers. Remember, always include their centers when calculating r. So if you're given a situation where you're given the altitude from the surface of a planet, we got to make sure we include the diameter, or excuse me, the radius. Okay, so there's our force at x. So using the same logic here, we say that the potential energy is equal to the integral of, now since r is the variable we're dealing with, I'm going to say the f of r dr, which is going to be equal to big G m m over r squared dr. And just to make it a little more easy to integrate, I'm going to move the r squared up. I'm going to say the integral of g m r minus 2 dr. And if you integrate this guy, you get g big M little m r to the minus 1. You add 1 and divide by the same number, or the way it's usually written is this. G minus g m over r plus our constant. Okay, so what's this constant when you're dealing with this form here? Well, the whole argument was that we want to find out where potential energy is 0. So that happened to be when we're on the ground level. When y is 0, that gives us 0 gravitational potential energy. So if you take a look at this equation right here, when will this go to 0? It'll go to 0. Now the g, m, and m are all constants, so the only thing we can take a look at is the r. Is when we make r really big, in fact if we make it go to infinity, this term will disappear. We'll have 0 potential energy. So really, when we are out in infinity, when we're out, let's say this object is out in infinity right now, potential energy is 0 when r is equal to infinity. So if this object were out at infinity, very, very far away, this is not the scale obviously, when this is at infinity, we would have zero potential energy, which makes sense because if you take a look at this, when you're at infinity, the force is zero. You have no force acting on you, you can't move. You have no gravitational potential energy. So using the same analysis here, like we did over here, this happens when we have minus g m over infinity plus a constant. So if you take a look at this term here basically goes away. Our constant is zero, and the final result on this side is ug is equal to minus g m over r, m times n over r. So this is the new gravitational potential energy equation right there, and that's how we got it, using the same analysis we did here. So this is the equation you'll plug into the gravitational potential energy bucket when we do conservation of energy. Works the same way, okay? The only thing that might be a little odd is that it's in negative. You have negative energy. So let's take a look at that. So I'll compare these two things here. So let's say in this case we have 0 joules here, that's the ground level, and we have 1, 2, 3 is right there. We have 3 joules, okay? And in this case, this would be, the reference line is here, so this is 0 joules. And let's say that it falls to the earth, just like this falls to the earth. And let's say this is negative 1, negative 2, and over here is negative 3. This would be up a little further, but we have negative 3. So basically I'm counting 0, 1, 0, 1, 2, 3, and then 0, negative 1, negative 2, negative 3. So let's compare the change in potential. What I want to show is that this negative sign, which is kind of weird, it just arises because of the integral, but in everyday usage it really doesn't make a difference. So I'm going to say, I'll do it right here, when this ball falls to the ground, the change in potential is the final minus the initial, which is equal to, let's see, the final is 0, because the ground down here, the initial is 3. So the change is minus 3. I lose 3 joules of energy. Okay. On this side, the change in potential is equal to the final minus the initial. So let's equal to what? The final is negative 3, right there. The initial is 0, because it's right there. And so the final answer is minus 3. I still lose 3 joules of energy. So this shows how, really, if you want to go from 0, 1, 2, 3, or 0, negative 1, negative 2, negative 3, the change is what we're really looking at, and the change is the same. It's the same actual numerical value. It just depends where we start. So this is a brief analysis of our old gravitational potential energy function, which is fine when we're close to the Earth, and the new one, and how the constants work in, and how to make sense of what negative energies are. Really, it's just a mathematical thing, but other than that, we can use this same equation in our gravitational potential energy buckets when we use energy buckets.